Air-ground robots, AGRs, are widely used in surveillance and disaster response due to their exceptional mobility and versatility, i.e. flying and driving. Current AGR navigation systems perform well in static occlusion-prone environments. For example, AGRNav uses 3D semantic occupancy networks, i.e. SCONet, to predict occlusions for complete local mapping and then computing Euclidean signed distance field, ESDF, for path planning. However, these systems face challenges in dynamic occlusion scenes due to limitations in perception networks' low prediction accuracy, high inference latency, and path planners' high computation overhead. Our key insight to address the above limitations is to propose an efficient 3D semantic occupancy network that ensures real-time inference while improving prediction accuracy. We draw inspiration from state space models, SSMs, and their improved versions, such as Mamba and Mamba 2 networks. By integrating Mamba blocks into a new 3D semantic occupancy network architecture, we aim to enable the network to model long-distance dependencies and perform parallel feature learning. This approach facilitates real-time occlusion prediction in highly dynamic environments, resulting in more complete local maps. Furthermore, while Zhou et al. Developed an ESDF-free path planner for quadcopters, it does not address AGR-specific requirements in dynamic scenarios, particularly energy efficiency and dynamic constraints. Consequently, exploring ESDF-free AGR path planners is also crucial to improving overall navigation performance. Based on these insights, we introduce Omega, consisting of two key components, OCC Mamba and AGR Planner. OCC Mamba, the first 3D semantic occupancy network based on state space models, SSMs, departs from previous networks that jointly learn semantics and occupancy by separating these predictions into different branches. This separation enables specialized learning within each domain, improving prediction accuracy and fully leveraging the complementary properties of semantic and geometric features in the subsequent feature fusion stage. We also integrate novel SemMamba and GeoMamba blocks into these branches to capture long-distance dependencies critical for semantic accuracy and occupancy prediction. By projecting features into the bird's-eye view, BEV, space, we reduce fusion latency to achieve real-time inference. Prediction results are merged into the local map using a low-latency update method from AGRNav, ensuring an up-to-date and accurate map in highly dynamic environments. During the planning phase, we propose AGR Planner, which builds on EGO Planner for aerial-ground hybrid path planning, to address AGR-specific requirements, particularly energy efficiency and dynamic constraints. We add additional energy costs to motion primitives involving aerial destinations, promoting energy efficiency. Simultaneously, we account for AGR's non-holonomic constraints by limiting ground control point curvature. Finally, by integrating the obstacle distance estimation method and back-end trajectory optimization, AGR Planner generates ESDF-free, energy-efficient, smooth, collision-free, and dynamically feasible trajectories. Our experiments were divided into 3 parts. First up, we evaluated OCC Mamba on the Semantic Kitty benchmark, comparing its accuracy and inference speed against the leading semantic occupancy network. Then, we put Omega to the test in simulated and real dynamic environments and pitted it against 2 AGR navigation baselines, showing off its superior efficiency. We looked at efficiency metrics like collision rate, movement time, planning time, energy consumption, and so on. The experimental results show that OCC Mamba had the most advanced performance on the Semantic Kitty benchmark, with an IOU of 59.9, MIOU of 25.0, and FPS of 22.1, which is 20 times faster than the network based on 3D CNN and Transformer. In the simulation experiments, Omega achieved a success rate of 98% with the help of OCC Mamba's real-time occlusion perception and AGR Planner's efficient ESDF-free path planning. At the same time, since there's no need to calculate ESDF, the planning time was reduced by 89%. We also conducted real-world experiments on our customized AGR. In navigation experiments across 5 different dynamic and occluded environments, Omega could achieve an average success rate of 96% and consume the least amount of energy. These extensive experiments not only verify the overall efficiency of Omega, but also validate the performance of its 2 key components, OCC Mamba and AGR Planner. Thanks for watching.